In this video, we continue our discussion of the ideal gas law by discussing its connection to the kinetic theory of gases and then looking at how we can make some modifications to adjust for real gas behavior. There are several basic assumptions that go into the kinetic theory of gases. One is that particles, atoms, molecules, it does not matter what, are hard spheres, more or less like billiard balls. We assume that all collisions are elastic, meaning that kinetic energy is conserved during collision. Again, this is just like billiard balls. When billiard balls collide, the kinetic energy is the same before and after collisions. That there are negligible interactions between our particles, and that the particle size is negligible as well. This, of course, is consistent with what we said earlier about ideal gas behavior. In addition, we assume the kinetic theory of gases that particle motion is random. So now we'll look at how the kinetic theory of gases allows us to derive an expression for pressure. We need to start with basic definitions. Of course, pressure is equal to force divided by area. And of course, in SI units, force has units of newtons, area will be meters squared, and newtons divided by meters squared gives us the SI unit of pressure, which is pascals. You may remember, of course, that other units of pressure, probably what you typically use in general chemistry, would be atmospheres, also bars, which we'll talk about later, is equal to 10 to the 5th pascals. And 1 bar is real close to 1 atmosphere. Again, we'll be discussing this later. Force is defined as mass times acceleration according to Newton's second law. And acceleration is equal to the derivative of velocity with respect to time. This means that force in the x direction is equal to the mass of a particle, times its derivative, the velocity derivative with respect to time, as we see here. Now, we also know that momentum in the x direction is equal to mass times velocity in the x direction. And that means that we can make a simple substitution here to show that force is equal to the derivative of momentum with respect to time. There is a direct relationship then to the expression we had above. And again, P here, for those of you who are not used to this, we use the symbol P to represent momentum. Okay, now that we have a basic definition of force and knowing that pressure is equal to force divided by unit area, then we can begin to develop a model that allows us to generate an expression for pressure. We'll start with just a single particle colliding with a wall container. The momentum of the particle before collision and in the x direction is simply mass times its speed, velocity in the x direction, and of course after the collision it has reversed its direction, and so the momentum is negative mvx. This means that if we calculate the force, where force is related to the change in momentum with respect to time, we have this expression here. The change in momentum is equal to the momentum before minus the momentum after. So plugging these simple expressions in, we get an overall change in momentum to mvx, and that means the force is equal to 2 mvx divided by delta t associated with the time. Okay, so going back to that previous slide, we found that the change in momentum associated with a collision with the wall of a single particle was 2 mvx, and that the total force, if we have multiple particles, the total force associated with multiple collisions with the walls of the container is simply equal to 2 mvx over delta t, which is the force associated with a single collision, times the total number of collisions. That should make sense to you. The total force is equal to the force imparted by a single collision times the total number of collisions. Of course, we're assuming at this point in this expression that the speed of every particle in the x direction will be the same. We'll make a slight adjustment for that at the end of our derivation. Clearly, they're not all going to have the same velocities. Alright, so now we need to just figure out, well, okay, we've got the force imparted per collision. We now need to figure out the total number of collisions. And that's going to be equal to this expression here, where we're going to take n sub d, which represents the number density, and multiply it by the volume in the container. That number density times the volume will give us the number of particles, and then we're going to multiply it by 1/2. The reason we're multiplying it by 1/2 is that at any given time only half of the particles are going to be moving toward the wall, the other half are going to be moving away from the wall. So there's our expression for the number of collisions. So if we know the number density and we know the volume, we'll be able to calculate the force. So the question is, what is the volume, and how do we determine that? The key here is to remember that force is equal to the change in momentum imparted during a particular time delta t. Alright, so if we set up our box here so that the distance that a particle travels in a time delta t is going to be equal to v sub x times delta t. We know that all particles within this distance here traveling toward the wall are going to collide with the wall during that time delta t. Alright, let me repeat that. All the particles between here and here traveling toward the wall are going to collide with the wall during the time delta t. Regardless of what that time is, that's the key. Alright, that means that if we have a box with a wall of area A, okay, then the volume of that box is going to be, again, the distance times the area. So here is our volume, alright. The distance, of course, is v sub x times delta t. Velocity times time gives us distance. And taking the area times that distance, we get the volume of our box. Alright, so now computing the force, we get this expression here using our expressions, where we'll note that, of course, we have the 1/2 nd from the number of collisions showing up down here in the box, in this expression, and we'll note that the volume of the box shows up here. And then, of course, we have this that is the force associated with the collision of a single particle. So we have multiplied the force per particle times the number of particles that collide with a wall in a time delta t. Of course, looking at this expression, we can see that the delta t cancels out since it's in the numerator and the denominator. That's why we don't really need to specify an exact period of time, because it cancels out. We'll also, of course, note that the 2 cancels out here, and we're left with an overall expression for the force equal to this here, where we have the number density multiplied by mv sub x squared times the surface area of the wall. Now we can begin to get an expression for the total pressure by taking the force that we derived on the previous slide, right here, dividing it by the surface area here, and of course we'll note that the areas cancel out, so the surface area was also not important. So we get an overall expression for pressure related to the number density, the number of particles per unit volume, times the mass of the particles, times the speed of those particles squared, or the velocity squared. Alright, now, of course, remember earlier I mentioned that we were initially assuming that all the particles had the same velocity. If we just make a simple adjustment here, rather than using the single value for all particles, we're just going to simply substitute the average velocity, what's called the mean square speed of the velocity, for that expression. Okay, and so we have that. Now we'll also note here that we have taken the number density and we have changed that to this expression here, which is just simply the number of moles times Avogadro's number and divided by the volume. So again, remember, number density is the number of particles per unit volume. We're going to take the number of particles. If we take the number of moles multiplied by Avogadro's number, that gives us the number of particles. So we're simply substituting number of moles, little n, times Avogadro's number divided by the volume for the number density, and we have this expression that we see at this point. Now we're not deriving this here at this point, but one thing that's important to note is that in the 19th century, Ludwig Boltzmann derived an expression for thermal energy relating the kinetic energy of a particle to the temperature, and this is the expression here. 1/2 kT is the thermal energy, the average thermal energy of a particle, where K is the Boltzmann constant. So if we replace mvx squared in our previous expression with kT from the thermal energy from the Boltzmann expression, we get an expression here which shows the pressure is equal to the number of moles times Avogadro's number divided by the volume times K, the Boltzmann constant, times T. Now it turns out that Avogadro's number times the Boltzmann constant is equal to the gas constant, and that gives us then P equals nRT over V. So it's a nice little derivation of the ideal gas law just based on simple kinetic theory of gases, which allows us to calculate the average force per collision of particles with the wall, and therefore calculate the pressure associated with those particles colliding with the wall. I think that's kind of neat. Okay, now that we've actually derived the ideal gas law by using the simple kinetic theory of gases, we actually can then go on to discuss the behavior of a real gas. Now again, remember, ideal gas law assumes no interactions between the particles and a negligible particle size. This curve here shows the intermolecular potential. That's V sub r. This is a potential energy associated with r being the distance between two particles. In this graph, we actually have two curves here. One which is shown by the yellow line, which is called a hard sphere potential. And you'll notice the behavior of this hard sphere potential is that at large distances, the potential energy, say way out here, potential energy is equal to 0 for the hard sphere potential. And then at some finite distance, which is actually 0 here on this graph, that the hard sphere potential rises to very sharply with actually an infinite slope. It rises to infinity. This would be what you would expect for billiard balls. At large distances, the billiard balls, of course, don't interact with each other, and that when they hit, when they collide, boom, they can't get any closer than that, and so this is what we expect for the kinetic theory of gases, that we have this infinite potential when r is equal to 0 for these billiard balls. Now, that of course is not reality. A better description of real behavior is illustrated by this red potential energy curve here, where we'll see at large distances the potential energy again goes to 0, but as the particles get close to each other, the potential energy drops. And that negative potential actually is indicative of attraction. Attraction is a negative potential interaction, and so we see that dip that gives us a negative potential. We'll call this actually sometimes a potential well when the potential energy drops, indicative of attraction. Of course, as the particles get closer to each other, potential energy starts to rise again and actually goes very sharply, although not with infinite slope, but it does go very sharply up. And that again is due to repulsion between the particles as they get too close to each other. So what we need to do, if we're going to have an expression for gas behavior that includes both attraction and repulsion, we're going to have to make a few modifications. And one expression that we'll use, and we'll see some other expressions later in the semester, but one that makes the most sense intuitively is what's called the van der Waals expression, and that's this expression right here. If you look real closely at this expression, you'll see that it bears some resemblance to the ideal gas law. You do see the nRT over V, but now you've got these additional terms here, this NB term, and this term out here, which is subtracted from the first term in the expression. This second term that's subtracted from the first term actually is representative of attraction, and this parameter A that we see here is a parameter that represents the degree of attraction between the particles. It is subtracted, and this should make sense to you, as particles are going by each other. If they're attracted to each other, it's going to reduce their speeds as they go by each other, and therefore reduce the force associated with collisions with the walls of the container. So attraction actually serves to reduce the pressure. If there was no attraction, the speeds would be higher. They collide with the walls of the container with more force, and so we'll note that this attraction does tend to reduce the pressure of the gas. We'll also note in this expression that it depends on density. This dependence on density here is shown by the N over V, moles per volume. That's a density expression, and it's dependent on the density squared for reasons that we will discuss later on. The B term in the denominator of the first one is something called the excluded volume per mole, and it actually represents the absolute non-zero finite volume associated with the particles. Remember, the ideal gas law assumes negligible particle size, and it assumes essentially that the particles are points in space with zero volume. The B term serves to compensate for that. What this means is that when we take the total volume of the container and subtract from that the total volume occupied by the particles themselves, we take the excluded volume per mole and we multiply it by the number of moles that we have here, then the V total volume minus the volume of the particles actually gives us the free space within which the particles can move in the container. So the denominator of that first term, V minus NB, represents the total free space for particle motion. Now I can relate B, the excluded volume per mole, to particle size. It actually is going to allow us to calculate an approximate diameter for the particles in the gas. If we consider two particles represented by the red circles here touching each other, just like two billiard balls coming together, they can't come any closer, then their centers are going to be separated by a distance that's actually twice the radius of a single particle, or the diameter of a single particle, assuming that all the particles are the same in our gas. And we are at this point assuming that all the particles are the same. So again, we have the situation where we see the distance separating the centers when the two particles are in contact is equal to the diameter of a single particle, d. Now it's important to note that because the particles can get no closer to each other than that, then if I take the particle on the outside here with the little arrow that we see and kind of move that all the way around this other particle that's in the center, there will be a sphere, that's mapped out. And the volume of the sphere is going to be 4/3 pi d cubed. All right. Again, d would represent the diameter of a single particle, or in fact the radius of the sphere as we move this first particle all the way around the second particle, that this particular sphere is such that no other particle can come within that, no other particle center can actually come within that sphere. That means there's a region of space with a volume 4/3 pi d cubed per pair of particles in which no other particles can move. This may be a little bit hard to understand. You might have to think about this a little bit, but that's what that represents. Now, if we take that volume per pair of particles, so again that was 4/3 pi d cubed per pair of particles, and multiply that by Avogadro's number, we get this expression here, which represents the volume per mole of particles into which other particles are not allowed to move. That's why it's called the excluded volume. It's a volume that excludes all other particles. So this B value here is equal to 2 times Avogadro's number times pi d cubed. D, again, is the diameter of a single particle. So if we go into the lab and we collect data, pressure, volume, temperature data for a gas, we can actually use that data to determine the excluded volume B, and from that determine the actual diameter of the particles in the gas itself. Again, this assumes that the particles are spheres with a diameter d. Now, what's key about this particular equation, of course, is it does represent a more accurate expression for the behavior of a gas. But remember, the ideal gas law was independent of the identity of the particle. What's notable here is that every different substance is going to have a different attractive parameter A and a different excluded volume parameter B. So now we have an equation that depends very much on the identity of the gas, and we'll need to look up those values of A and B in data tables in order to calculate any pressure associated with the van der Waals gas. So again, A and B are dependent on the identity, and you will need to look up the specific values in a data table corresponding to the gas for which you're trying to do calculations. So this ends our discussion of topics brought up in Chapter 1 of our textbook. We'll move on to Chapter 2 in the next video.